Welcome to episode 2 in the series on simulating molecular water on a computer. In this episode, we will learn how to code the central part of our program, known as the solver. This helps us solve the equation of motion. But first, let's install Julia. If you do not have Jupyter Notebooks, download it via the Anaconda package. Then open Julia and install the iJulia through the package importer. Open a new notebook and select the Julia language. Before we program our solver, I want to point out why the choice of solver is important. Consider the spring with a mass attached to it, a system known as a harmonic oscillator. The equilibrium position of the spring is at x0. And the energy of the system can be described by a quadratic potential, where k is the spring constant. If we solve this system analytically, we see that the spring performs a simple oscillatory motion, described by a sine wave with a constant amplitude. If we want to solve the spring system on a computer, we have to consider the equation of motion, given by this formula. The force is mass times acceleration. It is more suggestive to rewrite it in this differential form, where acceleration is written as the second derivative to the position. The force, F, is then given by minus the first derivative of the energy to the position. Since a computer is digital, we have to chop up our timeline in small steps, similar to a movie consisting of separate frames. We start with the position of the mass at some time t, and calculate the position of the mass at times t plus delta t, each time increasing the time by a small amount. For each time step, we solve the equation of motion. A simple way to do this is to use the Euler solver. With this technique, one calculates the next time steps with respect to the current time step for both the velocity v and the position x. The force can be seen to appear in the equation for the velocity, and the velocity appears in the equation for the position. Here, the letter h represents a very small number. When the computer solves the equation of motion using this technique, indeed, an oscillation can be seen. However, something strange is happening. The amplitude increases with time. Moreover, when we look at the total energy over time, we see that it increases, contradicting the conservation of energy. This has to do with an error buildup in the Euler solver. A good solver should respect the conservation of energy. We will therefore use a solver known as the Velocity Verlet integrator, specifically designed to respect energy conservation. It's given by this formula. Note how the acceleration also appears in the equation of the position. The computer now calculates the trajectory correctly, producing a sine wave with a constant amplitude. If we consider the total energy, we observe that it is constant. Well, almost constant. If we zoom in, we see that the energy performs a very small oscillation, but this is not important, as long as it doesn't blow up. Now our spring system can be happy. Okay, it is clear that we should use the Velocity Verlet solver. But this was just an example for one dimension, with one single particle. What do we do when there are 3 dimensions and hundreds of particles? How do we structure our data? The simulation of the spring system worked by filling up a one-dimensional array with values of the position of the mass over time. The same was done for the velocity and the acceleration. Now, since our water simulation will be in 3D, we will need to store values for the x, y, and z components. This will be done for the positions, the velocities, and the acceleration, leading to 9 different arrays. Each of these arrays must also contain the information for all the atoms, which demands an additional dimension, giving us 2-dimensional arrays. Consider, for example, the x position. Each row contains the values for one time step. Recall that we will simulate water, which consists of 2 hydrogen atoms and 1 oxygen atom. I choose to fill the matrix first with pairs of hydrogen atoms and then to continue with oxygen atoms, shown here for 2 water molecules. Our arrays will initially be filled with zeros, given in Julia by the zeros command. The amount of rows will be equal to the amount of time steps, and the amount of columns will be equal to the amount of atoms. We will first define the arrays for the positions of the hydrogen atoms. Here, n describes the amount of water molecules. Note the factor 2 to account for the double hydrogen atoms per molecule. We can then do the same for the arrays containing the velocity and the acceleration information. Now we introduce the arrays for the oxygen values. In this case, n appears singular in the definition, as there is only 1 oxygen atom per molecule. We then initialize the first row of our arrays, setting the positions, velocities, and accelerations at the first time step. We will come back to this function in some other episode, but for now let's just imagine that the arrays have been initialized in some way. We are ready to merge all the matrices using the cat function. The arrays are ready to be filled, and now we can finally code our solver. We will start by setting up a for loop, which will help us to make steps through time and to fill up that sweet position array. This for loop must contain the 2 steps that define the velocity Verlet method, starting with updating the position and ending with updating the velocity. We also include a little progress tracker. It would be nice if this was all, but after studying this for a while, one figures that everything seems to depend on the acceleration in the next time step. In order to calculate this, we need to force on every particle, which is obtained via the gradient of the energy for every particle. The fact that this must be done for every atom means that we need to include a nested for loop that loops through all the atoms. Note how the gradient of the energy only depends on the position of the atoms and not their velocities. We're now ready to put our money where our mouth is and to code the operations. This is pretty straightforward for the velocity Verlet equations, keeping in mind that all 3 dimensions must be taken into account. For the gradient of the energy, we write a function, which takes the positions of the next time steps and an index keeping track of the atoms. This function will be explained in the next episode. The acceleration at the next time step is then obtained by dividing the mass of the respective particle. This concludes our solver. In the next episode, we will learn how to program the gradient of the energy via a function. See you!